Well, good afternoon. Welcome to the last session of TechEd 2004. My name is Carlson. I am the Director of Technical Strategy in the Platforms Business Management Group at Microsoft. I work primarily working with our operating systems teams and with hardware partners on advanced systems and advanced architectures, developing the technical strategy and identifying really where Microsoft products fit in and where the holes and the gaps are that we need to address as far as our architectures and operating system features and functionality. I've been at Microsoft 17 years, started on Windows 1.05, and was also the lead support engineer for Microsoft Flight Simulator. And that happened to be one of the best jobs in the company. The best presentations that I've done have typically been as a result of questions that I couldn't solve on my own, and I had to sit down and research and spend some time working on it. It just wasn't something that fell out and said, okay, here's the answer. So in my background, I've done things like network interoperability, where you sit and build all the networks, become an administrator, and get familiar with all the tools to figure out how we do network interoperability and solve these type of problems. In the networking space, that was one thing. But when you go to hardware and you start talking about 64-bit architectures, you start trying to say, okay, who's on first? And how do we compare these different architectures? Because now there's this push moving forward of 64-bit architectures. Some have been out for a while. Others are just emerging into the marketplace. And all of a sudden, you're expected to have some idea or some comment on, what is our strategy for the companies you represent or provide consulting for? And, which 64-bit solution should I go with? Because there are multiple vendors in the marketplace providing these solutions. And at the same time, there are different price points and different advantages of the different architectures. And so that's the result of the result of that question is really this presentation, because our engineers inside of Microsoft need to know, as well as our customers, to say, okay, how do these things really compare? And it ended up being 197 slides. No, we're not going through 197 slides, I guarantee you that. But I did boil it down to really what are the salient points and how can we look at it. It's certainly not the definitive way of how we look at this data, but I think it gives you an idea of, that's a very interesting points about how 64-bit architectures compare and how they're different. So obviously 64-bit computing is not new to the PC platforms. The DEC Alpha, many years ago, working on Windows NT, we were supporting DEC Alpha. Sun Ultra, with Ultra Spark architectures, and then the one on the PC platform was really Itanium. Was Intel ships Itanium in May 2001. Microsoft had Windows available with that, and we've been working with Intel as they've developed the Itanium processor architecture to have operating systems Windows platforms that run with that. And then most recently, April 2003, AMD ships Opteron, and then the children that follow that, the Athlon 64 and its variants of the FX and the mobile platform. 64-bit machines enable high-performance computing, giving us abilities to use larger word size and larger address spaces, especially when we start thinking about doing floating point or these areas where we have very large data sets of very complex numbers, and we're really trying to figure out where the needle is in the haystack, and we need to do a lot of processing of complex data sets. So the focus of this discussion is really going to be about Itanium and the x86-64 internally to Microsoft. In fact, I may slip it. That's x64 as we discuss it internally, but certainly the industry understands it as x86-64. And when we talk about x86-64, it refers to two platforms. One being provided by Intel, as they call it, the Extended Memory 64 technology, or EM64T. AMD supports x86-64 in their Opteron, Athlon, and Athlon FX51, FX53, and the M technologies. But this battle or the challenge about 64-bit platforms is really taking two distinctly different strategies. And that's really where the question came in from my point of view of saying, how do you compare these things? One strategy has been to use the EPIC, which is a variant of a very large instruction word architecture versus the complex instruction set. And that's the strategy that you see between Itanium and x86-64. Then you also have Itanium competing in the high-end 64-bit space. And that's really where the background of Itanium is really based in the days of like 97 and those type of days where servers were being built faster, bigger. We're really competing on the high-end server space because there was no end in sight to what servers would need to be able to do. I mean, this is just as the dot-com craze and all the servers started going crazy. And HP and Intel got together and said, hey, how do we solve these problems and how do we design an architecture for the future that we can really expand upon, and how do we do that processor design? AMD, on the other hand, used the former Intel strategy of migration. And instead of just saying, okay, we're going to kind of throw away the x86 architecture and we're going to start with something new, AMD basically took a page out of the old 16 to 32-bit migration strategy and said, we're just going to extend the 32-bit architecture to 64 bits. And that would give us backwards compatibility and an easier migration path, as these 32-bit applications and operating systems would still run on what was then called the extended 64 architecture. But it's not just about processors, because it's about system architecture as well. And that's where the data that we're going to present at the end of the session is very, very relevant, because we're going to show you two different architectures, how they vary, and then take a look at what the results are in practice as far as what type of benchmark data supports that. So the R&D started in '94, HP and Intel. They went down the path where they looked at within the processor and said, how do we architect the processor to be the most powerful, most feature capable, and most scalable that we can do? And they really focused on parallelism, that type of strategy. And they optimized it using predication, speculation, and then using instruction level parallelism to really figure out how can I take advantage of hardware architectures to make as many parallel paths to reduce the misses and the branching that has to go on within the processor. So today when you use CISC architectures, you typically use prediction, or they do things like gang loading applications and then gang loading the instruction sets into the memory of the computer, and then using a caching architecture to get the instructions and to load them in and try to get the biggest blocks of data or of the instructions in, so that we will hit it in the cache and not have to go to main memory to try to find the next instructions. Well, that's okay, but you mispredict about 5 to 10% of the time. And the problem is when you miss the cache, you have to go all the way out to main memory and go get the next instruction, or maybe even have to go out to the disk, depending on how your application's written. So that really slows the processor down to try to go out and get all that data. So Intel used a different strategy here and said, let's use predication. And predication basically allows you to execute both sets of instructions at the same time, to be just in case I might need to use them. So I have the result of that calculation standing by, ready to go. And when it comes to that point, I don't have to take a clock cycle to figure it out. I've already figured that out, and I'm ready to continue on. The decision has basically already been made. So that allows you to remove many of the branching strategies that are involved with that. And in using predication, you can get rid of over 50% of the branches, and then over 40% of the mispredicted branches. So there are some serious optimizations that are capable here. In addition, Intel also took a look with Itanium and said, let's use speculation. And speculation says, instead of going out and getting data from memory when we need it, let's go out and say, we'll load it as soon as we know we could need it. And we'll speculate as to whether we need this data or not, but we'll load it earlier on in the cycle, because load operations will take 2 clock cycles. And instead of having to go through all of those clocks to do the load, we'll simply load it earlier on and do it in parallel, so that that data is also sitting in a register, because the Itanium architecture has a very large number of registers available. A lot of this comes down to the fact that the processor speeds have been increasing at such a rate that memory can't keep up. And so you'll see tricks and techniques being used by the processor manufacturers in the CPU architecture, where they're using larger and larger on-die caches. Right? So you've seen the L1 and the L2 cache grow. Then there's the emergence of the L3 cache, continuing to try to get memory closer to the processor, because the memory speeds have not increased at the same rate as the processor speed has, and so they've been compensating for that. So speculation also helps address this problem with slower memory. So one of the examples that are really documented, and I'll keep this as short as possible, but this is the 8 queens loop. And basically what you want to do is place 8 queens on a chessboard so that they won't attack each other, right, by the previous queen. So you have to look for a clear spot on the chessboard to place the queen. And fundamentally, we don't want to go into how you place a queen on a chessboard, but I really want to look at the algorithm saying, okay, if you look at the process, there's 13 cycles and 3 potential mispredictions. And without any modification using typical programming, here's where we load basically where you check on the same row, then you check the diagonals. A and C checks the diagonals. Then you load it, the data that's in R1, you load it into R2, and then you do a comparison. And this is your prediction here, or your prediction here, where you have P1 and P2. P1 is if the comparison is true, P2 if the comparison is false. If there is no other queen on that row, in this case, then I'll go ahead and exit because I found a safe location to place the queen. If not, then I'm going to go down and check one of the diagonals, the A diagonal, and if there's no queen, then I'll go down and check the other diagonal. So that's what the algorithm does. But here's the data you want to look at. Okay? The mispredictions of this is 43% in the first incarnation, 33 in the second, and 39 in the third. So there's a lot of chance for mispredictions to go on, and a lot of opportunities for failure in slowing down the process. When you apply speculation to the example, and here's where Intel is really focused with the Itanium, how do we optimize this? Instead of these separate opportunities to go through the load cycles that you see in step 6 here, or in 10, okay? And by the way, you notice it goes from 2 to 4 here. That's because the load cycle takes 2 clock cycles. So they're really optimizing here by avoiding these 2 clock cycles in block 6 and these 2 clock cycles in block 10. And instead, you see the load S, and that being speculation. We'll go ahead and load them in parallel in step 2. Okay? This is not rocket science, but it's how you get optimizations at the processor level. Now you have 9 cycles with 3 potential mispredictions, as opposed to 13 with 3 potential mispredictions. Now you step to the next level and add predication. And notice that we have predication already calculated here for P1 and P2. And what you do here is, previously in cycles 5 and 7, you needed to know P2 and P4. We can go ahead and branch off of that based upon the data here in P1 and P2, and we can go ahead and load this in block 5. By doing that, we basically go out and reduce the mispredictions by 2/3, and when you look at the number of mispredictions, you're down to 16%. And through the combination of combining the predication steps in 5 and 6, we're now down to 7 cycles with only 1 potential misprediction. Okay? That's where the Itanium, they really focused on looking at processor architecture and processor design. Okay? So Itanium has some very intelligent use of parallelism and parallel architectures with basically 2 floating point processors sitting inside it with a number of registers available that can easily be used and rotated to do a lot of purely computer science elegant programming, and to have compilers take advantage of all the resources that are available. And that's where the Itanium really has a strong suit. But now let's take a look at the system architecture, because how fast your computer runs and how your operating system and the applications produce results is based not only on your processor, but also the system architecture. And that also plays an important role in the results that you'll see running at the keyboard or running a server or what have you. So if you work primarily with software, this may be new to you. Certainly in my previous work at Microsoft, I spent most of my time in software, and it took me a while to come up to speed on hardware. But if you're familiar with hardware, this will basically review basic system design, but I want to make sure that everybody kind of understands what's going on inside your box. So the basic architecture is you have a processor sitting at the top of the tree, and this is Intel architecture. So you'll see this very typical type of design for 32-bit processors. So your processor is up at the top in orange. Then you have the North Bridge. And the North Bridge is connected to the processor by the different data buses, right? So the processor is connected to what's called the North Bridge, also known as the memory controller hub. And the North Bridge is responsible for taking care of the different services and system calls that would service fast devices, okay? One of the fast devices would be memory, for example. Another fast device that has migrated from what's called the South Bridge to the North Bridge because of its speed has been the video support. So AGP4 and AGP8, for example, are typically coming off the North Bridge. So if you're moving data, for example, from the processor to main memory or vice versa, you go from the processor through the North Bridge and then over to the memory controller. Okay, so there's 2 jumps it has to take in order to get that memory, either to or from the processor. Then connecting the North Bridge to the South Bridge is another bus. And the South Bridge handles all the I/O operations, and typically the slow data operations. So it's called the ICH, or I/O Controller Hub, but you'll typically see it listed as the ICH. And that handles devices of a slower nature, such as storage devices, network devices, typically below a gigabit Ethernet, for example. Your BIOS is coming from their sound, and the PCI bus and ISA bus, if you have an older architecture machine, come from the South Bridge. And that's how the basic architecture of the PCs work. Okay? So if we take a look at it in a real sense, if you look at a Pentium 4 architecture, this happens to be with the Kennerwood chipset. This is an Intel diagram. You have the P4 connected to the north bridge, right? And this is a 875, otherwise known as Kennerwood. And you have 6.4, 4.2, or 3.2 gigabytes per second transfer rate that you can move from the processor to the north bridge and then turn around and send it at 6.4 gigabytes per second to the DDR memory, the dynamic data RAM memory with dual data rates. So this would be your typical flow in that architecture. Similarly, you have your video, you have your communication streaming architecture for gigabit Ethernet is now off the north bridge instead of the south bridge. And then you have your slower devices, so your BIOS, your network, what have you. So that's a typical diagram that you might see. Now, when you switch to Itanium architectures, you'll see a lot of similarities between an Itanium architecture at a system design as you will with a 32-bit architecture. So you have your processors lined at the top, and this way it's a 4-way Itanium processor. Then you have a system bus that handles 6.4 gigabytes per second transfer rate to what was the north bridge, which is now a scalable node controller, which is in essence a switch to be able to communicate with memory. So you have your large array of memory sitting off the side, you have your processors at the top, your north bridge. Your server I/O hub is basically your south bridge, and that can connect to multiple sets of PCI devices, so large data arrays, large drive arrays, what have you, for large storage systems. And here is kind of, for backwards compatibility, here's your ICH4, which is the previous generation of the controller hub. So you have scalability here at 6.4 gigabytes per second per port that you're connecting to, but that's how the architecture works. Okay, so it's not rocket science, it's just a different way to do it. But you'll notice that as you add more processors on board, you're creating a bit of a bottleneck opportunity here because you're moving so much large data to the scalable node controller that a bottleneck can occur at these type of points. So when you look at system architecture and performance, you start trying to figure out, okay, where am I moving large amounts of data? How large are these data blocks? And where might I actually start to see performance issues with regard to bottlenecks? Typically, we see it when we're running 32-bit machines. We're typically seeing loading an application being delayed by the disk. Right? It's not your processor that determines necessarily the speed of how fast you load the application. It's typically how fast can I get it off the disk. Now, once you've loaded the application and you minimized it and you want to do something with it, now it's coming from main memory. But a lot of times when you start an app, you'll typically see it being delayed by the disk. Now, one other thing I need to mention about the Itanium architecture is also the 32-bit application support. And that is different from Itanium 1 to Itanium 2 because Itanium 2 now supports the IA32EL, or what's called the IA32 execution layer. And the reason for the execution layer is to provide fast, performance-oriented support for the other types of applications that you might need in an Itanium solution for an enterprise environment. So you might find an Itanium version of SQL Server or other type of high-end software for large server operations, but typically the 32-bit applications that also support it, like management and enterprise management tools, antivirus, some other type of tools, backup and recovery is another good one, that aren't supported directly on Itanium, but you need to have a performance-oriented solution that is compatible with these systems. And that's the purpose of the IA32EL. And that is basically will give you performance of a 1.5 gigahertz Xeon running on that system. So the IA32EL allows us better compatibility and better performance than the hardware implementation in its predecessor. So it allows you to use the SSE2 instructions, for example, but allows you then to use native Itanium applications for the best performance alongside 32-bit applications for management and other system-level tasks. Just a couple of notes, and I won't spend time on this, but running Windows on Itanium, the driver must match the operating system release. The drivers are an extension to the kernel, so therefore they have to match. Most 32-bit applications will run in the WoW32 layer. You can download the IA32EL driver from Microsoft.com. And then 64-bit applications, you can either do the work to take a powerful application to the Itanium platform by doing the development work to support it in 64-bit native instructions for Itanium, And that would detail that you typically have to understand a little bit more about Itanium architecture for the performance areas of the code. But if you're going to do heavy floating point, it's definitely worth it. In other cases, you can take advantage of the .NET framework, which we'll be releasing, currently scheduled for Q4 this year, that will run on Itanium as well. So any application you've developed for the .NET framework will simply just run on Itanium. And that's one of the benefits of the .NET framework, is it doesn't matter really what you're running on. You can just run it on the framework, and it will JIT it to that native architecture. So Itanium summary, developed by Intel and HP. The current product is what they call Madison. It's a 6 megabyte cache that they have on board. There's developing a 9 megabyte cache for that. The momentum is really focused on the high-end server applications, on the databases, and high-performance engineering class applications. The economic conditions have slowed the uptake after the dot bomb happened. And then the improvements to the Xeon processor have also kind of pushed it up, because the Xeon is certainly not out of gas. And so as Intel continues to develop that, the Itanium sits above typically Xeon, or at least that's what we think, that Itanium sits above Xeon in that space. And we take a look and ask more of the data, and we'll see that for the most part that's true. So that's kind of a quick peek at Itanium. But now let's look at something completely different. And this is where the problem comes in, right? Is when you take a look at AMD, right? Because AMD has taken the IA32 architecture that Intel developed and innovated and what have you, and they have extended that using the x86 64 extensions. AMD, of course, the spin-off from the Intel clan in '69. Basically, they did second sourcing of chips. And they had kind of life in the shadows, and it really wasn't a lot of pleasantness in that area, but they were determined. And they have developed Opteron and its follow-on Athlon as a bet the farm strategy around 64-bit architectures and improving the performance of the PC platform. So they basically took the play from Intel's book. They used a 64-bit migration that would allow enterprise customers to run 32-bit apps and 32-bit operating systems natively on the x64 or the x86 64 box. So that if you go out and buy an Opteron or you go out and buy an Athlon 64, you can install 32-bit Windows on it and 32-bit applications. It'll run happily along, not have any problems. Okay? So that gave them a migration story that some enterprise customers were looking for. So that was an advantage. And then they added a few engineering advances to make it more attractive for the OEMs. And frankly, it's pretty interesting what they've done. Now, when AMD took a look at it, they kind of did some analysis and said, let's take a look at what are the performance factors at the system level. Okay, where Intel really looked at the processor and said, how do we optimize the processor? AMD took a little bit more of a holistic approach and said, how do we fix the system? Number one, CPU speed makes the subsystems appear slow, right? It's slow to get the data out of the memory. It's slow to move data on the bus. It's slow to move this thing around. So the bus architectures aren't improving at the same rate. Multiple CPUs aggravate the problem because I'm trying to move data around on limited buses where I have collisions can occur. And I'm waiting to be able to move my data from a process to another, or I dump the cache on one processor and have to move everything over to another machine or to another CPU. But multiple CPUs are really where the servers really take off. So how do we fix this problem of collisions on the buses at the same time? I really want to have multiple CPUs. And then we need to also try to figure out how do we solve memory problems, trying to move the memory around. So they kind of looked at it and said, gee, how do we do this better, right? Or at least, how do we design an architecture that gives us an alternative? So I/O bandwidth has not kept pace. In fact, fast peripherals, when you get into USB 2 and you have these high-speed devices, if you put too many high-speed devices on the USB 2 ports, your devices are going to be colliding on the bus because the bus can't handle the bandwidth. I mean, that's today, right? It's easy to overdrive your PCI bus today. So AMD's different approach said, okay, what's causing the bottlenecks? We'll look at the processors, main memory, and I/O devices. But we realize that it's not necessarily just the processor. It's how do we design the system. So for case in point, one ATA 133 gigahertz drive, or megahertz drive, can flood the PCI bus. It's one drive. So if you're pulling data off the drive and you want to do something else on your PCI bus, you can wait. Right? So like the network, trying to access something at the same time you do a hard disk. Right? How many times have you tried to access something off the hard disk and all of a sudden your network stopped? Right? And it's waiting. And well, that's what's happening. You've had a collision on the bus. So the basic architecture of the Opteron is, of course, the processor core, which you see there in green. as a 64-bit architecture that will basically break through the 4 gigabyte barrier for memory on the machines. At the same time, we're going to take the memory controller, right? Remember the North Bridge? The North Bridge contains not only support for accessing high-speed video and high-speed networking, but it also has that access to memory. So we'll take the part of the North Bridge that takes access to main memory, and we'll put it right on the processor. So that if you're trying to go from the processor to main memory, you only have to do 1 hop instead of 2. That's a neat trick. And by the way, we'll give it its own bus that will run independent of the other buses so that it will have unlimited access to that memory. So it'll only collide with itself. So I was like, that's an interesting option. Then they also put an L1 and an L2 cache on, recognizing that memory accesses were still slower than the CPU speed. But they also connected into a different type of a bus called the hypertransport, which is different than your PCI bus or different type of architectures. If you take a look at the hypertransport gives a few options that are very attractive to the rest of the industry. One, it's an open, a non-proprietary architecture, which means, for example, I don't have to pay royalty fees to whoever invented that architecture, right? So one of the things that have been a barrier for things like FireWire is that there's a royalty typically involved when you want to do FireWire. So one of the alternatives to USB 2, which is free of royalty, right? So this is, by using hypertransport, this is something that is an alternative, and it allows 1 or more fast point-to-point links. So if you have an array of 4 processors and you have a hypertransport connecting them, you don't have to stop at the intermediate processor. You can simply tunnel through that processor and go direct from the processor in the upper left to the lower right, and not have to pay the tax of going through the middle, right? So, gee, that's a neat idea. Then scaling the link with the clock speed. Because the memory controller hub is based upon the speed of the processor, the memory controller hub gets faster as the processor gets faster. So you keep stepping the technology forward. Make sure that the hypertransport also has PCI compatibility because there's a PCI to hypertransport bridge. There also will be a PCI Express to hypertransport bridge for those of you familiar with that. It is compatible then with the PCI interrupts as well as the new interrupt architecture many of you may be familiar with called message signaled interrupts, which is more of a software-based system. And then noting that hypertransport's been adopted by a significant number of startups that are really starting to build some momentum behind an alternative bus architecture. So this is very interesting. So what does it add? It adds 6.4 gigabytes per second per channel. You can have multiple channels. For an individual processor that can support up to 3 hypertransport channels, that would give you 19.2 gigabytes per second transfer rate coming off the processor. And that does not include the access to the system RAM, because that's on a separate hypertransport bus. Then Opteron adds a local memory bus, which will allow you to support up to 4 gigabytes of RAM per processor at 2.7 gigabytes per second per channel. So all of a sudden you've taken your processor, added on hypertransport links that will talk to the other processors and to the equivalent of your North Bridge and your South Bridge. Okay? Now notice that your memory controller hub is still now in the processor. And have a separate access from the processor to main memory. Wow. That's kind of an innovative type of thinking of how can we change the rules about what goes on. Now the current numbers for hypertransport for the existing architecture, hypertransport 2.0 will increase the speed from 19.2 to 22.4 gigabytes per second. So that's the follow-on specification. So if we take a look now at Opteron and Athlon systems, Opteron shipped April 22nd of last year, followed by the Athlon 64. The Opteron's positioned as a server processor. The Athlon 64 is a desktop variant. And then it runs the x86 32, in other words, the classic x86 applications natively. So you can run 32-bit Windows on top of an AMD processor, or you can run 64-bit Windows on top of an AMD processor. So it allows you that migration strategy, which is an option for enterprise customers, and kind of a neat way to look at it. So if you look at the architectures, now that we've kind of described the hypertransport and how it works, let's just look at something here. So if you look at a basic two-way Windows server, right, this would be more of your commodity two-way server. You have 2 Opterons connected by a hypertransport. Now this hypertransport is running at half speed, 3.2 gigabytes per second, because it's a low-cost implementation. right? And then you have main memory coming right off the Opteron, and this is coming off the local hypertransport. And then here are your other connections to the other hypertransports. Here's your north bridge, here's your south bridge, right? North bridge going over to PCIX through a legacy bridge, and then all of your I/O and your network devices coming off the south bridge. Extend that to an engineering workstation, and then you might add a AGP 3.0 tunnel to be able to support AGP graphics. Then you increase the bus speed to the full speed of the hypertransport, 6.4. Okay? And then you probably add another bank of memory on it because you're going to be doing engineering. You want to have a large amount of memory to be able to load all of these high-resolution data points that was for complex CAD-CAM type applications. And then off the north bridge as well, here comes the high-speed Ethernet adapters, right? So your gigabit Ethernet. Now going to a four-way server, now it gets more interesting. So here's where you start seeing what the hypertransport can do as far as connections. Here's 1, 2, 3 hypertransports all coming off that one processor, giving it the capability of 19.2 gigabytes per second coming off that processor. So literally there is no bottleneck coming off of this thing, right? You have a high optimized system here. And then having access to 4 gigabytes of memory off of each one. This is a little bit dated graph. It's actually PC 1600 to PC 3200 now. But I like the diagram because it does give a pretty clear definition of what's going on. But you can have a 4-way Opteron system all talking together. It's no difficulty for the one in the upper left to talk to the lower right because it simply tunnels through that channel. And then you have your north bridge, your south bridge, as before. So it's a very different way because instead of what has been classic architecture, where you have the main processor, your north bridge, and then all the memory off to the side, having to channel through those two hops and having a potential bottleneck, this is a different way of solving the problem where you have basically memory local to the processors. And so that you can have a very large amount of data sets available to that processor, and as long as you keep working with that processor, you're very highly optimized. Now, if you happen to do load balancing and take a thread and then move it to another processor, then you have to activate the hypertransport and move the data over. But that's really no different than what you do on a classic Intel architecture anyway. So it's interesting. Now, what AMD will say, and I have to do this, I kind of present an Intel point of view, present an AMD point of view. AMD will basically say, here's your bottlenecks on a one-piece system. Your access to your north bridge, memory access. I'm trying to get access to memory because it has to go through the north bridge to get over here, and it's only 6.4 gigabytes per second versus the capability of 2 channels at 5.4 gigabytes per second. And they've kind of identified, you can have bottlenecks here. When you go into a multiple system, I'm not going to step through this. When you go into a multiple system, this is where something really can occur. When you have all these processors moving data, it's more typical you could see a bottleneck at the north bridge moving those data sets across. And here's the alternative view. Okay, and I won't go into detail, but you can go ahead and read the slides if you'd like. But I think we've talked through most of the points. But what I want to get to, and here's really the interesting data. I spent more time than I should have on this presentation because I was very compelled by what data I was finding and how this looks. But what we want to do is, after we look at Itanium architecture, and after you look at AMD architecture, you sit there going, okay, wow, that Itanium optimization is really cool. I mean, I can save 50% of my instructions, I can do 64 data sets, I can do floating point. And then you look at the AMD architecture and go, geez, that could really be fast. And now what do, right? You're a director of IT or something, you're the one making the call. How do you compare? I mean, that's a question I was asking. How do I compare these things? So I went out and said, okay, let's take a look at a benchmark. And there's various benchmarks out there in the world. And none of this data that I'm presenting to you is going to be conclusive. But in the land of the blind, one eye is seeing. It doesn't mean I know where I'm going. It just means I have a vision. But the benchmarks, we're going to take a look at the spec benchmarks and compare them. Now, careful to note, spec int and spec floating point compare processor speed, just the processor itself. And then you get to spec int rate and spec floating point rate. And now you're talking about processor throughput, real systems running real type of workloads that the spec committee has said are representative workloads, either integer-based workloads or floating point-based workloads. And by the way, most of Windows operations are integer operations because all the window coordinates and what have you are all in integers. So that to give you some background on that. And then here's the disclaimer. This is just a view of the data. It's all publicly available. This is not, Ty's benchmark. This is not something that, I had a bunch of hacked up systems with, alpha code and stuff running on it. This is something you can easily do yourself. It's simply an alternate view of the data. And that when you design systems and what have you, there are a lot of other factors besides just performance and value, like reliability, availability, serviceability, heat use, form factors, cooling requirements, application of device compatibility, right? There's a lot of things that have to go into consideration. But let's just take a look at some of the data and see what we come up with. So I'm comparing 64-bit architectures and 32-bit, and I'll describe the top ones. I realize it's kind of an eye chart, but how do you get down from 197 slides? So I'll talk about the top ones, and of course, this presentation is available for you to review. And if you're interested in this, I would take a look at the data because it's quite interesting. So the top left and top right are matched, is what I want to comment on. So here's Spec Int performance. And Spec Int performance shows the Intel Pentium 4 Extreme Edition, 3.4 gigahertz, having the top position. Okay? The red bars, so the blue bars are 32-bit processors. The red bars are 64-bit processors. Okay, so it's not immediately clear that 64-bit's necessarily faster than 32-bit, especially when we do integer operations. Okay, so one thing to really note is that don't overestimate x86-64 as being like twice the performance of 32-bit processors. Frankly, they're not. Okay, at least they're not today. The initial advantage will be to applications that use large data sets because they have more memory availability to them. And that's where you'll see Intel talking about the extended memory aspect of their processor line as opposed to, wow, 64-bit is the world, right? So, that's what you're going to see initially. So more likely you're going to see like a 20 to 30% increase between similar Intel 32-bit and x86-64 processors, okay? So Pentium 4 EE has the highest integer performance. Now, what happens though, and this is just one way to look at it, but if you go out and take the Spec Int rating, which is relative to the other ratings, and divide it by the street price, okay, and these are street prices as of Thursday last week, so all this data is effective Thursday last week, so you know when the presentation was done, by the way. So you consider the Spec Int rating, and all of a sudden, here pops up the Pentium 4. Right? A 32-bit processor has the highest, if you take the Spec Int rating divided by the price, the street price, you show up, and the index for the performance over dollars on the bottom, and this will be consistent through the slides, and then the Spec Int rating is at the top. So you'll see the throughput in the blue and the red bars, depending if it's a 32-bit or 64-bit processor, and you'll see the value bars in the maroon or purple behind them. So as you can see, the Pentium 4 still has the highest value, but it doesn't have quite the highest throughput, right? And because here's the throughput over here as well. But you can clearly see that from a value point of view, the x86-64 processors are clearly a player in this space, and they're climbing. But when you're looking at processor architectures versus cost, was that the choice that you think would be at the top? Kind of an interesting thing. I would have thought I would have seen something like a 3.4 or something like that, a 3.2 sitting there. Now when you go to floating point, the data changes dramatically. At floating point, now look at the colors, right? 64-bit right at the top. So this is how fast are the processors themselves. Itanium wins the day, handily, right? So 64-bit fastest for floating point. But the x64 or the x86-64 is a close second. If you want pure integer performance, you're looking at 32-bit. But if you look at 64-bit, that definitely wins the day for floating point. Just pure performance. So if you're trying to design a system and you really need to have floating point performance, Itanium really has it. If you're not sensitive to price, Itanium's going to take it. But if you want to take a look at value, then we take a look at other data, and you see the Intel Pentium 4 2.8 and the 3.0 gigahertz show the best value. As you step down through that, you see that the 64-bit, in this case the x86-64s, are sitting handily in the middle. Itanium's a little bit lower down the chart. Now let's look at 8-way. Now we're going to go switch from just pure processors to systems, right? So we're now changing the benchmark from the spec int and the spec FP to the spec int rate and the spec floating point rate, which measure the throughput of the systems, right? So when we do throughput for integers, Itanium takes it, right? So 64-bit architectures take the high end on 8-way systems, right? So it's basically Itanium versus Xeon MP in this case, because there really are no AMD spec benchmarks for 8-way systems, right? So there's no x64 entry for an 8-way system. So really, in a Windows space, it's Itanium or Xeon MPs. In this case, Itanium has it, and for the best value, Itanium has it. But if you look at the value, Itanium shows the best value, but if you want to look at comparison with throughput numbers and what have you, the Xeon MP is also pretty close to what you see for the 1.5. So this allows you to take a look at that data. If you look at the 8-way floating point, Itanium. Okay, 8-way systems. Go down to 4-way. 4-way systems, we're looking here at integer 4-way systems. Integer 4-way system shows the 64-bit processors are definitely grouped at the top, right? You have the Xeon MP sitting here in the middle, but you have both the Opteron and the Itanium sitting high as far as as far as integer 4-way system architectures. That's pretty interesting, right? This is the Opteron 850, the Itanium 1.5 gigahertz, right? Now, if you look at 4-way integer systems as far as value goes, then you're looking at Opteron, right? The x64 architectures, x86-64. Now, I want to also specify that because Intel has not yet released their x86-64 processors, that this is more, it shows AMD, but this is going to be representative of the class of x86-64 processors. So I'm really comparing, what's, 64-bit, and then there's two variations, the Itanium and then the x86-64 class. And so I want to make sure to distinct that point, but the benchmarks are for AMD systems. We go down to 4-way floating point, Itanium, and then the x86-64s. The value is the x86-64s on a 4-way system. Okay? As you go down to 2-way systems, now 2-way starts to get interesting because 2-ways, 4-way server, you kind of think of that's definitely a server class machine, and that'll be typically it's a higher end machine because reliability, availability, serviceability, when you get to servers, you're not necessarily buying commodity processors. You're buying things that have stable image platforms and things of that order because you're really running the enterprise systems on these 4-way boxes. When you get to 2-way, it's kind of like, kind of the multiple boxes or the blade type servers that you might be running. So it kind of changes the equation here a bit. So 2-way integer throughput has mixed results. x86-64 has a slight lead, but 32-bit is also a strong performer. Right? So just because you're saying, wow, need to go 64-bit, not necessarily true, especially if you're doing integer type workloads. Okay? The Opteron and Itanium sit in there handily as well, but note that the 32-bit is pretty good. When you go into the value category, however, we're back in the situation of the x86-64 technology being more of a value-oriented solution if you're looking at that. And in 2-way systems, you might be leaning more towards value systems. Go to floating point, and Itanium again wins the day. And you'll see Itanium in multiple processor machine configurations is very consistently the leader in performance. So if you need pure performance, it's an Itanium system that will give you the pure performance. But if you're looking at value systems, then we start looking at different things. And not that it's only this clear, but these are just things to think about. So when you go to value in the 2-way floating point, the x86-64 technology takes the lead again, followed by the Xeon. Okay? So you want to think about what your workloads are looking like. And then data that I wasn't expecting. When we go down to 1-way 64-bit systems versus 1-way 32-bit systems for throughput, you'll see that the Xeon and the Opteron, of the x86-64 generation, are very, very close. So in 1-way systems, some of the times the 32-bit systems are very, very close competitors to a 64-bit system. When you start looking at value, you see the P4 3 gigahertz showing up again. as the best value when you look at performance benchmarks versus the street price. And then the Opteron and the 64-bit architectures are somewhat lower down on the chart when you get to one-way systems. So it's going to be a balance of what do you want out of 64-bit systems? Do you want pure performance? In which case there's a lot of options for pure performance. And then you have to balance that versus the cost, though, especially as you move down from high-end systems like an 8-way server. As you move down to a 2-way or a single processor box, is an x64 or x86 64 technology the best thing? I don't know, something to think about. Then we go down to floating point, and you guessed it, Itanium has it. But when you go to one-way floating point, Intel Pentium 4 3 gigahertz. So we're back to 32-bit architectures in a one-way system for floating point operations having the best value. And then you have the whole slew of x86 64 architectures. So that's kind of where those are at. So system solution requirements vary widely. These are just two considerations. But it might make you think about considering a force box system with two-way versus two four-way systems. When you start looking at, comparing the two-way, four-way, you can see that maybe a two-way system, a series of two-way systems might be better. Up to you. The road ahead. So now that you kind of said, okay, that's some interesting data, let's take a look at the road ahead. And how do we solve some of the problems I was just talking about? Well, first and foremost, and we're just around the corner from having PCI Express. So everything about bottlenecks on the PCI bus, for example, will go away. Or at least the vast majority of the problems with the PCI bus will go away as we move to PCI Express. It's a serial communication bus architecture. It is PCI compatible with the bridge. It's scalable. It'll allow up to 32 different channels of PCI communication at 500 megabytes per second per lane. In other words, 250 megabytes per second in each direction. So what you can do is you can simply add on the number of channels that you want to that PCI connection. And you'll hear them talk about a by one, a by two. So it's a PCI Express by 2, or PCI Express by 32. And they'll just refer to how wide that bus is. It's low cost, and it uses existing technologies. So PCI Express isn't really going to drive up the cost necessarily, but it gives us higher performance. And we'll see the initial systems out late in CY04. You'll probably see some early ones come out just around July, August. You'll probably start seeing a few reviews of these type of systems. What you'll see at first in is video. So AGP will go away. As far as new technologies deployments, there will be PCI Express. Typically, you'll see by 16 or by 8 type implementations. And so when you look at that processor architecture diagram we were looking at earlier, where you saw the CPU and then talking to the North Bridge, for example, instead of just having one connection going across, you'll just see multiple PCI Express channels moving that data through. So if you go over to your PCI Gaming Center a year from now, those are going to be PCI Express machines. Why? Because that's the fastest throughput from processor computation to the video graphics card will be through PCI Express. And that change at those high-end systems will happen very rapidly. So you'll see it first in gaming systems, and then you'll see it follow through in engineering workstations and what have you. But because the PCI Express is really going to happen kind of all at once as manufacturers start switching over, we can expect to start seeing these cards come out fairly quickly. So moving from PCI Express, trying to keep everything rolling here, moving from PCI Express over to Intel's 64, what they call their extended memory 64 technology processors. These were announced February 17th at Spring IDF, and there'll be the Potomac processor, which is the Xeon MP line, the Nocona processor, which is the Xeon line, the Prescott, some of you have heard it called various names, some of it called Yamhill early on, and then it went away, and there's a whole story there. That's the Pentium 4 family line. And these processors support SSE3, basically the extension, the 13 new instructions that came with Prescott. Also support hyper-threading technology. And I'll talk about hyper-threading here in a moment and when we talk about dual-core and multi-core, because that's on the road ahead here. So hyper-threading technology. It doesn't support AMD's 3D Now extensions, but that does not create a compatibility problem with Windows. So you get Windows, the same version of Windows, for the 64-bit extended systems will run on an AMD machine as well as they'll run on an Intel machine using the EM64T process. It's supported by Windows XP for 64-bit extended systems, which we currently have in beta. So we are supporting these as they come out. The next thing that you're going to see on the road ahead will be dual and multi-core systems, and this is going to be an interesting challenge. As you're aware, just ratcheting up the frequency no longer solves the problem of trying to design faster processors, right, for various reasons. One, if you probably saw Pat Gelsinger's diagram of not that long ago that showed that if we continue along the thermal course of processors, we'll shortly have the heat equivalent of a nuclear reactor on our motherboards. And so it's clearly we can't continue along the rate of condensing the fab design, right? We're going to 130 nanometers down to 90 nanometers and 65 and 45 and 22 and 17, and that's the course where we're headed. But as they continued shrinking the die sizes down, what originally happened was when you shrink the die size down, you get a heat increase of about 50%. But you'd have other economies of scale because of the smaller die size. Well, as you start getting down to these 90 nanometer and 65 nanometer, instead of only getting a 50% heat increase, you're getting something more like a 100% heat increase. And all of a sudden, you can't build a big enough fan or a heat sink, right? So all of a sudden, you start seeing these water-cooled things start showing up. How your desktop processor, and oh, by the way, here's your water jug alongside that you have to keep full to keep the processor cool. And oh, by the way, it gives hot water to your plants and all kinds of wonderful things, right? So one of the challenges is how do we go faster? Right? How do we make these systems faster? If I can't increase the triangle between power, frequency that you want to see of the system go, and then the die size, you can't keep doing that. So we have to do something new. And so you've seen kind of a shift in recent years, one from AMD and recently from Intel, where they start moving away from frequency of the processors to other types of numbering schemes to identify how fast they go, a relative numbering scheme. And one of the main reasons is because of the thermals. AMD is running AMD, and they'll talk about it, they're running a cooler architecture because they're silicon on insulator and things of that order. But nonetheless, they're both heading in that direction of running out of thermal room, right? The headroom's going away. So now they're switching into dual core, right? So what's happened is, when you went from like the Pentium 2 to the Pentium 3, they took additional ALUs, their arithmetic logic units, and just kind of threw them on, right? So, Pentium 2, I think they had 2, you get to Pentium 3, and something you have 3, and then you have a floating point unit in there. And they were kind of throwing the cores kind of inside the processor, and that's how they were getting additional performance as well as reducing the size, right? But how do you continue on with Moore's law? So now on a single die, they're simply going to put multiple cores sitting side by side, right? And then there's a whole question about, well, okay, now here's an interesting problem. Let's say that you have 2 cores and you're running on a mobile platform, okay? Now when you hit the power save button to try to reduce its speed, what happens? Do you tune down both processors or do you shut one off? Well, if you shut one off, what about the cache that it had? Or what if it was sharing a cache with the other processor? How do you shut them down? So there's a whole lot of mechanisms about how do we do dual core, right? Because it might share the same cache. So there's going to be a challenge here as we start going through it. But a dual core system will not give you twice the performance. Just as you've seen in the 2-way and the 4-way systems, when you start looking at the performance comparisons, when you look at a dual core or going to a 4-way or however many core systems that you're going to, you're not going to get a doubling of performance. Think more on the order of 20 to 50%, depending on the application you're running, depending on how you're using the system, depending on where the data is coming from, depending on how much the apps start switching threads one to another because you're loading the processor in a certain way. So that's the next step. And what you're probably going to hear, instead of multiple cores, you'll probably hear more about multiple threads. Because it may have 2 core systems supporting 1 thread each. And then you have 2 core systems that support 2 threads each. So if you just think about it as how many threads total they'll support, that will be how they start comparing. Most likely, that's probably how they're going to be comparing systems. So this is a 4-thread system, that's an 8-thread system, and things of that order. So that's how the road ahead looks there. So dual and multi-core systems will just look like multiple processors to the Windows platforms. Noting the performance increase, this does give you, though, an extension to Moore's Law. So from a system architecture, you'll say that the system's going to increase in performance as you go up. But now they're doing it with multiple cores sitting side by side. And that will also help them in the thermal situation, because if you run multiple cores, you don't necessarily have to run them as fast. So that does give them a little more headroom as far as the thermal issues go. So Windows XP today, just XP Pro or XP Home, supports 2 processors for desktops and workstations. So if you get a dual core system, there's no big deal to it. Windows servers support up to 64-way systems. So if you look at what the existing systems go, because now if I'm talking about dual and multi-core systems, I probably need to show you that yes, we actually do support that. So I'm not going to go through this, but I do want to highlight the bottom part of the chart here in the center, right? How many CPUs that are supported on the system. So professional 1 to 2, server 1 to 4, server enterprise 1 to 8, and then data center 1 to 32. As you go to 64-bit systems, that bumps up to 64 processors on the 64-bit systems. So as you go to dual core systems, that'll be fine. They'll just run faster. But that's the road ahead as far as where the processors are going. Okay, so we're going to see DDR2 memory. We're going to see PCI Express buses. We're going to see dual and quad core systems that are going to be running 1, 2, 4, 8 threads. You're going to see this happening on 32-bit systems, 64-bit systems as well. 9 out of 10, you're probably going to see a shift from the IA32 platform being the default platform that OEMs are shipping to seeing the x86-64 platform being the default that you can buy. And that trying to find an older processor like today's Pentium 4, for example, would be harder to find because everybody's just switched over to the extended technology systems or the Athlon 64, depending on whether you're buying AMD or Intel processors. But expect that transition to happen within the next year. That's how dramatic that shift is going to be. Okay? The reason why? There's not a lot of compatibility problems between x86-64 systems with your 32-bit applications and 32-bit operating systems. It has the same instruction set underneath it. Okay? So, and Microsoft is committing to supporting these type of architectures and making sure the device drivers and things of that order are certainly available as you run 32-bit applications on these systems. And we're working, as you may have heard if you've attended other events, Microsoft's also working very closely with the hardware vendors to make sure that 64-bit drivers are there for x86-64, because that will be a limiting factor if we do not have the support for those drivers. But when we're talking to the OEMs, they're all talking to us about x86-64 systems. Features that are not supported, by the way, in these systems, the Microsoft DOS subsystem is not supported in any 64-bit client. That's a real shame. I love it. I lived with it. 16-bit subsystems are also not supported. That also means that 16-bit installers to your 32-bit applications won't run either. So we're working with those vendors to actually solve that problem to get 32-bit loaders. And if we detect, the way we're writing it so that if we detect a 16-bit installer has been called, we'll actually go out on the internet through Windows Update to see if there is a 32-bit installer available and update the installer automatically so that the app will install and the user won't have an issue. We also are not supporting the legacy transport protocols. So old NetBEUI and some of these old lovely protocols that you and I have lived with for years are basically seeing their end of days. Other factors that are going to affect your 64-bit issues and migration and plans, right? First will be the fact that Intel's introduction of these processors with the extended memory technology and certainly their announcement of it, has validated this technology as an industry standard going forward. So the OEMs have clearly taken note and are making the appropriate plans. The compatibility with the 32-bit OS and applications, to the largest extent, not an issue. You will see it emerge initially as a gaming platform, then it will follow quickly by engineering class workstations, and then there will be a flood of them just being the standard machines that you can buy on the platform. PCI Express based video will be just a natural element of these systems, along with the high definition audio. Codename Azalea, if you're familiar with that technology, that's already in the system. as well as digital content creation. As you start seeing the Office applications and things of this nature, you'll see more digital content creation being involved with it. So multimedia type applications being more readily integrated with the applications and the day-to-day usage of the PC. Certainly, playing DVDs and things like that have already been done, but this will be more of an integrated type of experience. And then you'll also note that 32-bit application, and this is something that wasn't really expected, that when you take a 32-bit application and run it on a 64-bit system, an x86 64, it runs faster. Now, for those of you who lived through the 16 to 32-bit conversion, that wasn't true. Right? When you ran a 16-bit on a 32-bit system, it ran, but it wasn't a great experience. But in this case, this will make the migration process easier because of the 32-bit applications running faster even when they're running on the 64-bit operating system in compatibility mode. And we've seen this in the initial testing that we've seen on these systems. So you'll see, it's not a huge amount, but you're not seeing a degradation. So you're going to see anywhere from like 10 to 30% performance increase when you run 32-bit apps on the 64-bit OS. And the one thing that I think is an important message that Microsoft, and I've been involved in these discussions, I'm a member of the 64-bit strategy team at Microsoft. One of the things that has evolved fairly recently has been that Microsoft has committed in the 64-bit releases to support the mobile platform. And that's because the OEMs and company were very excited about what this could mean for the mobile platforms. So with AMD's introduction of the Athlon 64M, that puts a mobile x64 processor out in the industry. And Microsoft is committed to supporting, because that was not originally plan of record. But now infrared and the wireless device drivers and these type of things that weren't originally part of the schedule are now supported and now plan of record. And as this moves forward, then you'll see both competitive pricing and value opportunities show up in this x86 64 space. And basically, you have the opportunity to either take advantage of the x86 64 or the Itanium based upon what your needs are. Whether you need really fast floating point on high-end scalable systems, or you need to have an everyday workhorse, and depending on what your loads are, whether it happens to be an integer class load or a floating point load. Okay, maybe it's just, maybe you're doing web servers, stuff like that. Okay. So one of the things you want to do is you want to develop basically your own evaluation methods for the best 64-bit solution for your business needs, right? It's more than just performance and price. I just gave you a peek to take a look at the data a different way. Because to my understanding, and I looked out there, nobody had put this data together and say, well, who's on first? How do I compare these things, right? So this is just one way to look at it. Take into account the reliability, availability, serviceability, and these type of factors. There's a lot of difference between what service levels you can get on a four-way system that's built on Xeon MP than you will if you try to throw four inexpensive processors on it and call it a server and expect the OEMs to support it the same way they would a real server that's built with reliability and management and heat sensors and things like that in mind. Form factor, system architecture, etc. for peripherals. The best news as a customer, you have a lot of choices. I mean, this is great. You look out there and say, wow, I can run my 32-bit apps, I can run my 64-bit apps, or if I need really high-end systems, I have a solution for that too. And I have an ability to compare that and see what I want. Now, for developers, this is a really important point. If you develop development at part-time, or you happen to be the IT pro representing both your developers in your company as well as the IT environment, which I'm sure many of you are, is that you'll need to start writing your applications to take advantage of multiple threads. Now, to the most part, people think of doing that right now as like, okay, Word does it for background pagination, and we do it for spell checking, we do it for grammar checking, things like that, and that's only a high-end application thing. Not anymore. Multiple threads and designing for multiple threads in your application will be how your application will be successful and take advantage of the investment in these new technologies. So that your application needs to go out and figure out, okay, how do I spawn another thread so that this application can do this function while at the same time do network tasks in the background? Or if I'm going out and spooling something out to the disk, I want to automatically spawn off another thread to go do that, but I want to keep my main application thread still running and have, keep track of how many threads you're using in your system and use the priorities of the threads in your system so your application keeps the console running fast and then does, for example, the delayed write to the hard drive or to your cache on a as-available basis. So that's really the essence of what's going on. The references for the presentation, this is available for you. The spec information is available online. If somebody wants to have access to the Excel sheets that created all of this, my email is tycar, T-Y-C-A-R, @microsoft.com. Took me a few days to get all that together, but if somebody wants to see the source data, I'm happy to send it because it's simply specs data, and I'd encourage you to go out to the spec and do that. But if you want to see my background data, I'm happy to share that. The overview of the IPF architecture on the HP site, and the hypertransport architecture, the PCI Express architecture, and I did some reading on the PCI-X system architecture to compare the performance aspects of PCI-X, which is primarily a server technology to extend the life of the PCI bus in preparation for going to PCI Express. So that's really the information that I have. If you have questions, I'm open to that. I would ask that, being as this is the last session, if you wouldn't mind stopping by for the evaluations. If you thought that this was a waste of your time, please let me know. I'd be happy to stay home in Redmond. If you thought this was valuable and a different way to look at this data and help answer some of the questions, it may not give you the answers, but it gave you another way to look at the data. And this was the Win 318 session. And if you want to download the slides, they are currently available. I did have them posted. All right? So we'll close it. Thank you very much. Yes, a question. There it is.
Okay, when you compared to street price, was that the street price of the chip or the street price of the system?
Street price of the chip, where the chip was available. On one of the Itanium systems, I couldn't find the processor by itself, so I went and found the lowest price that I could of a good system on the network. It wasn't a used, refurbished, type thing, but it was the lowest price that I could find available. And I've documented that on my grid of where I found it and what price it was.
Okay, second question. The Intel extension is going to have the no execute feature.
The Intel extensions are planned to have the no execute feature in them, yes. In fact, that will, the Grantsdale G0 stepping and follow-on will have that. And we've tested it out and it works.
I have a couple of questions for you.
TICAR, T-Y-C-A-R.
First off,
yes.
in your, over here.
Thank you.
In your price performance analysis, why is it that the Athlon FX53 was not mentioned, as well as the Athlon XPs, which have a lower price and higher performance ratio than the other processors?
Because they weren't at the high level of spec benchmarks. So I went down the spec benchmarks and went down the highest list. So go out to the spec benchmarks, export them into Excel, do a sort based upon peak performance, and I went down to see the highest list, and I couldn't put 20 of them on there. I really wanted to compare what was primarily shipping, and unfortunately the Athlons did not show up. It was not an intention by my part. It was simply that those were either not submitted to spec for a benchmark result, or simply did not show up in the top. I tried to get 15 or something on them, but I'm sure some of you thought those were already iCharts already.
And I have one other question for you. You actually mentioned the Opteron 150 and the FX51, which are silicon completely compatible chips, but they had completely different spec views.
That's correct.
Why were the spec views different if the chips are identical?
Because of the caching, how they've implemented their L1, L2 caching algorithms.
Okay.
So they've got different, typically the size of the cache is typically what changes. And so they put on a large L3 cache. So you'll see the cache go from like 256 to 1 megabyte. Okay. And that's how the Pentium 4EE did it, for example.
All right. Thank you.
And they used a Xeon engine for the Pentium 4EE, by the way. What was next? Yes? No? Yeah, I can catch you afterwards if you need it. Tycar at Microsoft, Tycar at Microsoft.com. Better than any phone call. Guarantee it. Yes. Any other question? Go ahead.
Yeah, you mentioned that as this evolves, the developers would need to better understand the use of threading as well as the use of parallelism in order to better exploit some of the...
Okay, parallelism will be handled primarily by the compiler.
Okay.
But you do need to set up threads.
Now, here is my question. My question is, at the architect level, it might be, it makes sense to expect that they would understand the threading and how threading can be used for optimization and so on. But there are a lot of developers who are very good, capable developers. What kind of learning curve would be necessary, and whether Visual Studio or some of the tools, they can provide some kind of intelligent techniques within them so that developers who are not that experienced or that in terms of architecture and in terms of using threading can be able to move forward with using this?
There's a huge body of data, because I used to do support for the SDK for Windows in all those previous years. When we came out with Windows 3.0, we actually did a whole bunch of work on threading, and then we did it again with NT. So there is a large body of work already documented on threading. It's simply that developers aren't typically taking advantage of it because there's no real value for most applications. Correct. So the documentation is already there because I wrote some of it. Okay. But if you have questions, it's not a hard answer. Multi-threading is not rocket science. The only problem you want to worry about is if you're trying to write to the same memory, right? And then you have to do blocking and stuff on your memory.
Correct. The question is, when you have a team of developers for whom of different, competency level, currently you are able to create a large system and be able to give them different parts of that and say, okay, you go do that, you go do that, you go do that. Now, once you move to architecting things for the 64 level, how much of the same kind of methodology you are able to adopt versus how much do the developer teams need to be educated? Yep. In terms of how to exploit the threading aspects?
Okay, I'll give you an answer and then we probably need to move on. But the answer to that is have your lead architects for those different areas. How we do it at Microsoft is the lead architects all work together and they look at the system design and they identify where they need to set semaphores on memory. And they start doing performance analysis of who's going to get in my way. And if it's a really hard problem to solve, sometimes that piece of code moves from one area to another. Or it moves into your engine part of your application, because it is that complex, because they're really trying to optimize to the nth degree.
Okay, the semaphores you're talking about, are there, semaphores, are you using it as a metaphor where people decide, or are you using it as an operating system, the kind of semaphore that's technically used in operating system?
Right, it's not an operating system, but it's blocking, basically you're blocking the memory right, protecting the memory area. Yes?
You mentioned that you were expecting that gaming machines will lead the way. The question is 3D API support 64-bit, like DirectX, OpenGL?
Yes, we've made the OpenGL has been moved forward. The 3D Now calls are supported. I can't answer beyond OpenGL and 3D Now. I don't have that background. Yes? Oh, certainly DirectX. I'm sorry, was that? Yeah, DirectX is definitely 64. Sorry. I'm sitting here, well, there's other, Taiga and stuff like that, if you remember back to the old. Yeah. So does that answer your question? Okay. Any other questions? Yes?
Just a quick one. You had a bullet in there about Exchange. I think it was in your IPF description.
Correct.
You didn't really talk about that at all.
I didn't talk about, I was worried about running way over when I go into the details. The reason why Exchange isn't directly supported is because there's a 32-bit device driver for Exchange. Right. And the Exchange team is well aware of that, and we don't have an answer direct from them because Dave Thompson has just taken over the engineering aspect of it. So it's needed. I don't have an answer for you yet, but it is identified as a priority item.
I thought in this slide, though, you mentioned something about memory alignment. I thought it was deeper than just the 32-bit kernel driver.
Yeah, but the memory alignment is an easier problem to solve.
Okay. Thank you.
Yeah. Yes, that's correct. The IA64 is your memory alignment issue, but you still have that 32-bit kernel driver.
My point is not on your
if you want to give, I have a colleague here, Hakan, if you raise your hand. If you give that contact information, because Hakan also works on the 64-bit team, and he can actually take that information and make sure it moves to the right people.
One other question I have is just very quickly. Is there any differences from a Windows standpoint in terms of how memory is being addressed between Titanium Windows 64 and x64?
Is there any difference between how memory is being addressed between Titanium 64 and x86 64? From a virtual addressing standpoint, there would be no changes, no major differences, because when we go into 64-bit mode, we throw the x86 64 processor into native 64-bit mode as well. And so we have the virtual address space there. So we're running, the x86 64 has three modes, legacy compatibility and native, and we switch it into native mode, and it's a full 64-bit processor, and we use full address extensions there.
The pointers and everything like that are full 64-bit throughout x64.
Everything is fully 64-bit pointers with the exception of like 2 or 3 32-bit applications that I can't exactly remember. It's like media player. You know, there's like 2 or 3 apps that are going to still run 32-bit, but everything at the OS level is 64-bit. Thank you.
Do you see
Middle? Sorry. No, there.
do you see any issues running both platforms in a cluster environment?
Running the old platform in a...
No, both. Like having in a cluster 132.
Oh, in a clustered environment.
Would we need to like switch over file services, so on?
As
Testing?
long... In a failover, we're passing... Good, that's a great question.
Thanks.
I'd have a hard time supporting it. If I was the IT director, I'd have a hard time supporting it because you've got 2 support factors in there. But if I wanted to, as long as we're shipping over data sets and same data blocks, I'm really shipping over data and where I was at.
It's just for transition. Or
Yeah, for transition, it should work. There shouldn't. I'm going to have to caveat that in testing it because somebody might be throwing something across when the heartbeat fails, but they should be just throwing over the data sets and what the next call was, right? I was at this API with this data block. Here's the pointer to that data that I just shipped over, right? And you deal with it. So it should work, but I'm going to caveat that because there could be an exception that I'm not aware of. So I have to put that caveat on it. That's a great question, though, and I'll have to ask that as I get back. So if you want to ping me in about, mid next week, I'll have an answer for you. Okay.
You had mentioned in the slide presentation that the the new Prescott chipset was EMT64 compatible. Is that just because of the SSE3 instruction set?
No, it has to be. You have to have the right. It's not Grantsdale. It's Alderwood. Is the chipset that will support the new Prescott. So
the 64-bit
the
Prescott.
the Prescott EM64T will require the Alderwood chipset, and that's the current plan of record, and that will support the SSE3 and the SSE3 instructions as well as the NX and the other options that are turned on.
Isn't the Prescott chip a 32-bit chip though? Isn't it the same as the Northwood, just double cache and a couple other
Prescott,
instructions?
Yes, but Prescott also has more on board that isn't turned on.
But it's 32-bit still.
Prescott is a 32-bit processor, but it has all the x64 extensions already sitting on the die. The fuse is just burned.
I see.
So it's the same processor.
Okay.
That's how the technology goes. So as new technology evolves, oftentimes it has a home on the processor somewhere in the die, but it's simply disabled by burning a fuse. And we do that for testing and stuff like that. Then once it passes validation, that, if you remember the Pentium 5 floating point bug, or the P5 floating point bug, they had to go through all this validation. It was a huge recall. So Intel is extremely rigorous about doing all their testing. So until they've really validated all the functionalities there, they'll typically burn the fuse and still have a high-quality retail product that's the 32-bit processor. If they need to have the 64-bit extensions, then they'll simply enable the fuse, and you have that same processor is a 64-bit processor. Will run on a 64-bit OS. Okay, that's it. Thank you very much. I know it's late on Friday. Have a great weekend. Thank you for coming to TechEd.